So you can see my screen, okay?
Yes.
Okay, great. So a couple of points about who we are. So Sierra Circuits is a PCB manufacturer and assembler. So we have a building, or a series of buildings dedicated to PCB manufacturing. It's about 70,000 square feet. And then we have 70,000 square feet dedicated to assembly. So we're both. We're not an assembler that buys circuit boards from a circuit board vendor, or vice versa. So we do both internally, and that's led to a lot of improvements and a lot of internal accountability. So it's been a good business decision overall through the years. And we build very complex circuit boards. RF circuit boards seem to be a growing demand or a growing market. And high-speed digital as well. So that's who we are, and we do small, medium production and prototyping. And today we're going to talk about DFM, and DFM is obviously near and dear to a PCB manufacturer's heart. And a lot of feedback and effort goes into giving the right thought process to our engineers. And really, we see it as a partnership where the engineers and Sierra's engineers work together to get things done. So this webinar also is, goes along with our mission to educate engineers out there, educate our customers as much as possible to have a smooth business process for everybody. So DFM, I would say, has these kind of specific benefits, but understand DFM is not capability. It's more than that. So if you're looking at our website or someone else's website and looking at the specs of what's capable, that's step one. But DFM really is how things work together in manufacturing. So you apply design rules to your design, and then we'll look at the design holistically and the stack up to determine how manufacturable it is and what are the risk factors. If it's a prototype, a lot of fabricators just don't give too much feedback because there's no need. It's just a one and done. But if it's a design that's going to go through iteration, then that feedback is critical, especially post feedback, and asking the fabricator for the yield data can be very critical to improving your success, both in functionality as well as cost drivers in production, as well as performance. Something that came up yesterday, there's a order on the floor that we're building high quantities for, where they have a inner core, and the inner core was designed in a way that we were scrapping it. And so it's heavy copper, parallel traces, and a thin core. So, and it's special material, so that core is very expensive. So all these things were kind of stacked up against a fabricator like ourselves doing a good job on that inner core. And so that leads to delays and, cost. Either we priced it wrong, or we priced it correctly for us to be able to make a profit, which means that the OEM pays for the scrap. So if in early on stages, the fabricator, which we were not part of in this case, the fabricator and the designer work together to understand any issues on the floor, and frankly, should be instigated by the designers, then that feedback would have been given early on in the iterations of design improvement, which would save a lot of heartache for us and cost to the customer. So that's a kind of a real life example of why this information is important, and as a designer, what you should be doing. Okay, so step one is, have you supplied all the information that we need? Like having a complete data package is always an issue. So we're looking at many designs every day, and this is what comes up every day. So I recommend that you have a very strong checklist for the files you send us, and why those files are needed. And if you're not supplying a file, to call that out too, as to I'm not supplying this, you know. So just having a holistic view of the data you send us. That being said, ODB++ and IPC 2581, they're evolving, and it's one file that has all the information in it, and you don't have to worry about not sending us a particular file. So I highly encourage IPC 2581 and ODB. And there are viewers out there, so you can look at the data before you send it to us. They're free viewers. So I also highly recommend that. Netlist is also a big deal. When we get your boards finally to the finished state and we're testing, doing a flying probe electrical test, did we create our own netlist off of your Gerber data, or did it come built into the ODB or IPC file? And if it comes into the IPC file, much better. If the IPC file is included and we're not building it, much better, because we're then comparing to your schematic. And if you have any issues with your netlist, then, you know, or don't supply a netlist, we're not testing to your schematic. We're still testing, but we're really only checking to what the Gerber data is, which can be wrong. The next kind of overall point I want to make is, how do you select a material? We have a material selector on our website, and we're improving it every day. Customers will pick materials based on just the electrical properties and not look at these other key areas. So we're highlighting areas that maybe you're not looking at, which are just equally as important as the electrical properties of the material. So the thermal conductivity of the material, the CTE of the material, all these things are really important. And then we would, if you're not picking a specific material, we would pick a material that is consistent in X, Y, and Z as well. And the reason for us to pick that is because as we're building boards, board after board, we do what's called scaling. And so we would pick a material that's relatively stable, so that when we figure out or try and figure out the scaling before build, that we have a good database of that information. If we pick material that's cheaper and doesn't have good dimensional stability, it's really just messing up our own scaling database. And then the customer would also get unexpected results as well. So picking the right material, both from the customer standpoint and from the manufacturer standpoint, is a key part of the DFM. Once you pick the material, did you also pick it for the stack up? So again, a material just based on the data sheet is not good enough. So in our material selector, we have some more attributes to the materials, like, is this material suitable for blind vias and sequential lamination? Is this material suitable for solder mask? We have these extra pointers because picking a material by itself but looking at the data sheet by itself is not enough. For a manufacturer to onboard a material into their factory is not for the faint of heart. Not only do all the databases have to be updated correctly, but also the recipes have to be updated. So how are we drilling the material? What kind of plasma recipe are we using? Does it laser drill well? What's the scaling factor of the material? So all these things mean that the fabricator has onboarded the material properly. And so if a fabricator hasn't used that material or flavor of that material, they're not ready to just on your design, try a new material unless you have an understanding and agreement that, hey, this is what we're doing. Because things can happen that the manufacturer may not have been able to predict, like the scaling I'm talking about, or maybe like just how the material moves after lamination and things like that. So the designer can be helpful to understand, where are your cores and prepregs? Does that material flow well? And is it appropriate for your copper weights and your via structure? So knowing that upfront, and if you don't, talking to your fabricator to make sure that this type of a stack up is manufacturable, especially with those material choices, will give you a successful build. And that being said, we also have our stack up tool on our website, which will help kind of get you in the right place early on. So we're going to do a quick demo of that. And we're also improving our stack up tool and would like to ask if anyone would like to be a beta customer for the next improvement that we have slated. So if you're interested in being a beta customer, you could message in the Q&A or wherever, just let us know if you're interested in that. But this is the tool we have right now on our website.
Yeah, hi everyone. This is a Sierra Stackup Designer tool. It provides manufacturable and cost-optimized stackups and also includes an impedance calculator. It allows you to change the signal plane combination and the copper weights in the generated stackup. The tool also allows you to download the stackup data in IPC standard 2581. First, you need to start by entering these board information here. Let's go with the project name, a revision number, the length and breadth of the PCB. You can use this drop down here to choose the target PCB thickness. Similarly, you can choose a PCB material here. You can also click on this material selector compare guide to compare or view the data sheets of various materials, and compare their attributes. Next, you go to the stack up design method here and you choose the first option if you know the number of layers required in your design. And if you have a complex BGA that dictates the number of signal plane layers in your board, then you go with the second option here. Now, choose a layer count, a signal plane layer combination, and click on Run Stack Up Designer. You will be presented with the Sierra Circuits recommended stackups here. And it gives the stackup information like the layers, if it's a standard or HDI stackup, the sequential lamination, the thickness, and the technology level and cost index. You can click on this report button here to view the stackup that resembles your buildup. So in this page here, if you scroll on top here, you can view all the details that you had chosen before without having to go back to the previous page. And if you do any changes to the board over here, then you make sure to click on this generated custom stackup to update the stackup. You can scroll further down and you can see that there is a detailed construction of the stackup here. Here you can change the layer type. If suppose I change this plain layer to a signal or a mixed layer, we can see that the copper percentage is also automatically adjusted. We can remove this solder mask also from here by clicking on this cross symbol. And you can further scroll down and you have the built-in impedance calculator. Click on this plus sign here and you have added a fresh line of impedance. Here you can choose the signal layer. You can go with a target impedance. Let's go with 100 for now. And choose a model type. I'll go with differential pair. Then you enter the reference layers. And you click on calculate. So we see that the trace width, the trace spacing and the propagation delay, these are all calculated and displayed. You can click on this view symbol here to view the whole of impedance calculator tool. Now you can scroll on top and you can click on this save button. So by clicking the save button, you generate an ID that allows you to access the stack-up in the next login sessions. You can also click on this export to IPC 2581, which imports the data in a .xml file, which can be implemented to any ECAD tool, which supports IPC 2581. Thank you.
Okay, thanks. I just want to highlight again, the 2581 is a bidirectional format. And so you can start your design process by asking us for a stack up or using our tool on our website, which is free at the moment and has been free for many years now, which gives you, kind of a early kickoff on your design. Not all designs are the same, so it does help to start off with a tool like this. So thanks, Anjana. And like I said, we're getting better and better at the tool. You guys can see my screen, right? Okay, so I'm assuming that's a yes. So another big thing other than getting your stack up right and your material choices right is really understanding your drills. And so there's some key points here. You really, what we see as kind of some issues is that, you're drilling holes without proper clearances. You're drilling holes too close to the next copper feature, which is drill to copper. You're drilling holes too close to each other, which could cause failures in the field later on. There's something called CAF, and CAF basically means that when you're drilling the holes, there's all these micro fractures in the materials, and then the copper can migrate through the material, and in the future in the field you can have copper touching copper. And so what aerospace and military they check for is what is the extent of the micro fractures after drill, and that can't be too much because they're worried about what I just said. But everyone should be worried about that. If you're using the cheapest material possible and then you're drilling your holes very close together, no matter what the size of the holes are, I mean, this could be a real issue for you. So, following basic design guidelines is only part of it, but also picking the right material choices is also a part of it. What we like for the drills, I mean, I think every board shop likes this, is a drill the copper of 8. So the edge of the hole wall to the next copper feature. Those are for mechanical through holes. That doesn't apply to laser drills. Laser drills are much more accurate and they don't go through the whole board. So drill the copper is really less of an issue at that point. And, the next thing to understand about your drills is what tolerance do you have? Is there a component that's going into those vias? Then you need to you kind of need to call that out and make sure that the tolerance of the plating aligns with the connector, let's say in this case that I'm thinking. And if it's just a connection and you don't care about how much that via closes, then you can also state that as well. It doesn't have to be plus or minus 3 on every type of hole. And then aspect ratios mean that essentially can any fabricator see the inside of the via after drill? And can they properly plate a uniform, even amount of plating from the knee all the way to the center of the via? If the aspect ratio is too high, then you can kind of have bad plating or issues with the plating that don't meet the IPC class. So, that's kind of the reason to worry about your aspect ratio. There's also an aspect ratio consideration and hole size consideration for SANA fill. So if a via requires SANA fill, you should call that out in your drill chart, and then the fabricator should and would check for whether that hole size is conducive to the SANA fill process. And the aspect ratio is good for that. If you have any questions on drills, you can ask. We have a process engineer on the webinar as well. So the more questions you ask, the better. And if we don't know the answer, we'll always come back to you with that. Okay, so annular ring, I mean, it's always kind of the first question that customers or potential customers ask us. The designers are designing their board, what's a proper annular ring? And the answer is it depends on your design. It depends on so many things. What is the via being used for? If it's just vias for RF purposes, then maybe breakout's okay. And if it's a via that is for a connector, and there's specific tolerances that need to be met for that connector to be high quality, to have a high quality assembly, then that's a different via. So all these, the more you can call out on your drawings, the better you're setting up your fabricator for success. But knowing what are the proper annular rings to design to, and not every fabricator is the same. So for example, for us, over the years, we've replaced all of our drill machines with vision drill systems, where we're not just drilling we're basically drilling by looking at a fiducial or the next copper feature and then drilling each via. So it's a much more accurate drill. Where 5 years ago we had drill machines that were not vision drill. So there's a lot of fabricators that don't have vision drill. So knowing what tolerances they can handle and designing to that would be the least common denominator. But if you have any kind of high density board, it's okay to ask the fabricator, hey, do you have vision drills? Because it's kind of necessary. Let's see. Yeah, annular ring for class 2 versus class 3. We have an amazing blog on our website that talks about that. Just class 2 versus class 3 in general, and knowing that annular rings for laser drills are different than for mechanically drilled or the component holes that I was talking about. So we have all those guidelines on our website and in this presentation. So next biggest thing is, understanding your copper clearances. We still get designers that have copper going up to the edge of the board, which, you don't want, because when you're routing or finally cutting through your board, you don't want to cut through copper. So there's always a tolerance about routing, and I think we are plus or minus 2 mils on our mechanical route. But to be safe, for all fabricators out there, I would do plus or minus. Understand there's at least a plus or minus 5 mil tolerance potentially on mechanical route. Yeah, but basically understanding the copper feature to the edge of the board is key. And then going back to via design, how close can your via be to the edge of the board? In rigid flex, the via to the transition area has to be more because the material has to flow around the via, but also not end up on the flex area, which would reduce your bend radius on the flex. So that's a different design rule, but mostly, 10 mils to the edge of the board is totally fine. And here's some other kind of clearances. And then you want to check for impedance discontinuities. And if you want to achieve accurate impedance control, then you can avoid these common issues. First is make sure you tell us which traces are the high-speed signals. You can modify your trace width or spacing by 0.1. That really helps us find and highlight those across the whole board and all layers. We see issues with split reference planes, inconsistent spacings as the traces meander through the board. Those are all common issues that we see. So to avoid them, verify that you have continuous reference planes across the meandering of those traces, that you can maintain some sort of clear spacing. 3W is the best, but it's not obviously possible all the time. But at least being aware of it and maintaining that continuous spacing would be key to avoid, your impedance discontinuities. And so we're going to do a demo of our impedance calculator.
Hi again. This is a Sierra Circuits impedance calculator tool. It uses the 2D numerical solution of Maxwell's equation for PCB transmission lines and renders fairly accurate results. The impedance calculator tool supports 82 impedance models with multiple geometries here, such as the uncoated, coated, and embedded microstrip and the strip layer. Sorry. And with each of these specific models, you can choose signal, differential pair, coplanar. For example, you can see there are so many models available over here, and you can choose any of these combinations here to access your geometry models. I have opened some tabs here already to just show you that different geometries over here. Right. Let's go with coated microstrip differential pair impedance calculator for now. And we start by entering the input parameters. Let's go with the dielectric height. Sorry. Then we have the dielectric constant ER1. Let's go with 3.63. A coating height of 1.5. We have the coating height H2C and coating height dielectric constant over here, which already has a default value of 0.5 and 4.2, but this can be changed if you wish to do so. Let's add the coating height here again. And to calculate this trace width, we have to enter delta W. Let's go with 0.5 for now. Delta W is nothing but the difference between the top of the trace and the bottom of the trace, and you can use this reference guide over here to choose the value. Then we add the trace thickness. and a trace separation here, and enter a target differential impedance value. Click on calculate W. So this will calculate the trace width and the other parameters that you can see over here, like the propagation constant and the coupling coefficient, etc. If you want to do a reverse calculation, all you have to do is enter the trace width along with the other parameters here and click on calculate ZD. Now we can go to the signal loss calculator for the same chosen geometry. You enter the dissipation factor here, of frequency. Let's go with a surface roughness of 6 microns. This is a standard roughness for a foil and a length of about 2 inch, and click on calculate loss. The signal loss output in the odd and even mode will be calculated and displayed here. Now we go to the S parameter calculator. You have to enter the source impedance and the load impedance here. And choose one of the output, either complex or polar, and click on calculate S parameter. Since this is a 4-port network, we can see that we have a 4-port S parameter and a mixed mode S parameter matrix over here, and the characteristic impedance and the propagation constant are also calculated and displayed. One thing you have to make sure is to use this S parameter calculator, you have to use the signal loss calculator before, because the frequency that we have entered over there will be used for the calculations here. Then we have the crosstalk calculator here for the same model, and we can see that the geometry is also displayed. You have to enter the coupled trace length. Let's go with 2 since that's what we entered earlier. Enter the signal rise time. Let's go with 100 picoseconds, and signal voltage of maybe 2 volts, and click on calculate crosstalk, and the near end crosstalk and the far end crosstalk are calculated and displayed. Thank you.
Thanks, Bandana. You guys see my screen?
Yes.
Okay. So those tools are amazing if you're not using them already. I mean, having a crosstalk calculator, having, all these at your fingertips, and free is amazing. So I think the engineering team has done a great job in setting up designers for success and continue to improve the tools, which is it's just amazing. So, another area that we want to talk about is, having proper grounding and shielding. Very important for RF design. And actually, we have other webinars and resources completely dedicated to this, and also seminars completely dedicated to this, with experts in the field ready to talk to you about your issues. So, take advantage of that resource that Lucy's putting together for you guys. Anyway, so, you want to make sure that when you're doing via stitching that you do it properly along your ground planes with a lambda over, let's say 10, to ensure a low inductance return path. And you want to make sure your copper cores are grounded correctly to prevent the EMI issues. And then if you can have any kind of shielding, that would be great. Shielding to sensitive traces and areas of your board. These are the best practices. And like I said, that one slide doesn't do it justice. There's whole seminars on the topic. Next is, solder mask. Because we're a fabricator and an assembler, we're not looking at solder mask just from a PCB standpoint. We're looking at it from both an assembly standpoint as well. But solder mask is an important part of the process and important for assembly. You want to make sure you're setting up your fabricator for success. So having a 4 mil solder mask dams, is universal. Everyone should be able to achieve that. We can get down into 2 mil solder mask webs, but talk to us for that. Make sure it's conducive for that. Now, just having your solder mask 1-to-1 with the outer layer copper is a start, but certainly not the finished product. If you leave it to us, we would do a global solder mask clearance of 2 mils larger than the copper features. The next is that you want to understand what is your copper weight and what are your solder mask thickness requirements. If it's a heavy copper and you put a note saying we need 1 mil of solder mask thins out over the peaks of the copper. And so if you have that 1 mil requirement, we're going to have to double coat, maybe triple coat. These things take time, cost more money, and can reduce quality. No one likes to double or triple coat a PCB. So be careful to know what your 1 mil minimum note means on the solder mask. Second, you can have solder mask slivers, and so solder mask slivers can be an issue. Hard to manufacture, they can peel off, things like that. Also, you have to make sure that your material that you're picking is conducive to solder mask in general, and what kind of features can it hold as well. And rigid flex and flex is a whole different topic on solder mask and what kind of openings that you need. Are we using LPI for your flex areas? That would be a question to ask us or any other fabricator, and that would have different rules and tolerances as well. So, and then of course, next is silkscreen. Silkscreen dimensions can, be posted as an issue prior to manufacturing. You don't want overlapping text features. There are people who don't want any silkscreen on their board at all because they've seen defects because of silkscreen. So be careful of your silkscreen. Make sure it's not falling on a pad. Here's some general guidelines as well about, what you should look at before sending everything over to us or any other fabricator. One thing key, which I didn't really mention in the solder mask is we're seeing a lot of, because we're doing fab and assembly, we're seeing a lot of areas on the board that should be free of any kind of defects or let's say FOD or anything. Definitely no solder. But if there's a mask opening, then you can have those issues. So please call out things on your drawings of any kind of critical sensitive areas. And here's a quick checklist for your fab notes. I think one thing to note is that if the board's going into space, you should probably call out outgassing requirements on your drawing, on your fab drawing. And whether the board is going into space or not, you should always ask for a cross section of your board so you know that the right plating was used, the right thicknesses are there per class 2 and per class 3, and enough material between copper layers so you have a sense that the board was built properly. Those should always be there. And so we follow a very rigorous DFM process in our manufacturing, prior to manufacturing. So, I'd say that's one of our best features as a fabricator. So take advantage of that. I highly encourage that, and work with us early on in the process and you'll get a better design overall. So that kind of summarizes it. We have a lot of resources that we work hard on that subject matter experts are looking at and it's contributing to not just at Sierra, but also outside in the industry. So we're really working hard to get you the best information, you know, for you to, make the best decisions for your designs. So with that being said, I think we're ready for questions.
Yeah, Amit, you can check the chat. There are a few questions.
Is Steve Carney on?
Yes.
He might give a nice technical answer to these questions.
Okay,
And then,
I'm here.
okay, great. Lucy, do you want to read those questions out to him? You can answer them.
Steve, we have, okay, so first of all, if anyone has new questions, please use the Q&A and not the chat. But right now we have two questions in the chat, one by Wilfredo. For traces, is to constrain the layout based on, I'm not sure that's a question. Okay, then we have another one from Trevor. Do you have a standard Altium design rules file for fabrication with Sierra? If not, is it possible to have a meeting with Sierra to review?
Yeah, we like talking to people about their designs and what they want to do. I'm sorry, I'm trying to follow your questions here. So which question are you on? I'm sorry.
It's a second one in the chat. People are using the chat. Please do not use the chat. Use the Q&A.
Oh, design rules. Yes.
Okay, the answer is yes. And
Yeah, so as far as the design rules, so what we've laid out here is basic fail-safe design rules. We do a lot of we can run things a lot tighter, and we have different sets of design rules, but everything has to be set up for that up front. There's different material sets that are available now that help support like sequential lamination, higher densities, higher speeds, tighter drill to copper, those types of things. So if you look at the design rules and go, okay, I need something tighter than that, definitely give us a call and we'll be happy to discuss what you want to do and come up with a solution if there is one.
yeah, Trevor, you have my email. If you want, you can send me an email and I will set that up for you. And Steve, there's one more question in the chat and then we're gonna close the chat. Is it enough if I just send one file for IPC 2581 for both fab and assembly? That might be a question for Amit. Amit, are you still here?
I am. Yeah, I'm also trying to follow which question that is.
It's the one on the bottom at 1045 from FX.
Yeah, it's one file, 2581. That's why it's so good.
Okay, now let's go to the Q&A. And you should be able to see the questions. Can we plate the via with 2 mil copper?
Yes, we can do that. There's a couple ways to do that, depending on what the end result wants to be. So the standard process is we do what's referred to as a pattern plate, where we plate the copper in the holes along with the traces on the surface. So if you want to do that, you want 2 mil copper in the hole. First, you have to make sure that your finished hole size is big enough to accommodate the 2 mil. And then the 2 mil in the hole, it's going to build onto the surface. So say if you start with a like a 1/2 ounce copper on the surface of the panel, you're going to end up with 2.7, almost 3 mils on the surface and 2 mils in the hole. The other way, sometimes for thermal vias, things like that, we can do a separate drill file and do what's referred to as a barrel plate, where we just plate those specific holes with 2 mils of copper, and then do a secondary process to do the rest of the plating. So obviously that's a whole nother set of process steps, so that's more money, but bottom line is yes, we can do 2 mil in the hole.
Okay, next question. What are the key parameters to review for RF PCB?
I mean, really so typically, you know, RF boards are, they have a tendency to be, you know, wider traces, more plain areas, things like that. But I think mainly the main parameters for RF is material selection and stack up. So basically what RF materials, you typically get into like PTFE, Teflon, ceramic filled Teflons, those types of materials. So it's really just, you know, looking at the stack up and make sure that the materials support the RF designs.
Okay, thank you. Another question. What are the Sierra requirements for DFM on traces, solder, mask, via aspect ratio, a 2 to 5 page condense have, interested in a condensed 5 page of your preferred, rather than 50 page books? Okay, I'm not sure I understand the entire question, but Steve, I think you can answer the first part.
I don't know what they're asking exactly.
What are our requirements for DFM regarding traces and solder mask and aspect ratio? I guess that's a question.
We'll create a create a two-pager and send it over.
Yeah, so traces, solder mask, aspect ratio, those are actually different topics.
We'll create a summary. It is a big guide, so we'll create a summary so people can digest it easier.
Okay, next question. Does Sierra do non-magnetic epic plating? Is that
Yeah.
epic plating?
Yeah, we do that.
Okay, another question. Can Sierra do any plating with leaded solder? And if not, what platings are available?
That is more of an assembly question.
Yeah, it's fine. I think the answer is yes.
Okay, but we'll confirm. I will post the Q&A in a few days in the Sierra Connect thread. So check that in a few days. Okay, yeah.
So yeah, we do lots of back drilling. I can't address how it affects cost. Back drilling would be specified in the fab notes. Our machines use a electronic feedback system. So we actually, it forms a connection between the top of the panel and the tip of the drill bit. So the advertised control depth with these systems is plus or minus a 1/2 mil. So typically we see closer to plus or minus 3/10 of a mil. So it's extremely accurate.
I'm sorry, was that the answer to the back drilling question?
I'm sorry?
Which answer was this for which
So that was for the back drilling.
Oh, okay, you answer the back drilling. Okay.
Yeah, so yeah, we do a lot of back drilling these days. So again, it's in the fab notes and plus or minus a half a mil depth tolerance.
Thank you. Wilfredo, I'm not really sure what you're trying to ask, but if you want, you can unmute yourself and you can ask your question directly. I think it would be easier.
No, my question wasn't related to serial requirements, the preferred serial requirements of your capability, because design can vary. Now, if we had to vary the design based for a specific requirement, then it's basically when we need to go and talk about a one-to-one for the design, but instead of having these 50, 68 books, I rather sometimes prefer, condensed versions, 5 pages. These are my requirements. These are my preferred requirements. Anything outside from this boundary, let's talk about one-to-one. We know that really cost really increases based on the features and things like that, right? I work for the aerospace industry, and cost many times is not an issue, but performance, especially in harsh environment, because we have basically things need to be protected right on the space, and really payloads is one shot. A workshop doesn't work upstairs, right? So because many times it's not an issue, the cost usually becomes an issue in commercial, industrial, sometimes in the automotive, right? So the important thing is sometimes we are packing those boards and we have minimum requirements many times, right? But for a class type 3, right, high reliability, sometimes there are some guidelines really there. But also there are some also guidelines in what the manufacturer like Sierra can do. So the 2 to 5 pages is the condensed version. It's what is your capability and what you prefer to.
I get
And
it.
then anything from that boundary is a discussion, design by design, which take more time.
We'll do that. I think that's a great suggestion. We're gonna do that.
Yeah, I'll make a note. Raul, can you please make a note? So basically, we need the DFM handbook in 5 pages.
Or less.
Yeah.
Yeah, because many times, you go through all these, they're different. I love your design book also too. And also, there's another company that you're already aware actually has a ton of design books, and you will see them in the IPC. I know you're going to be in the IPC. We have been chatting with Lucy many times, many years, right? So, and I know that the other company has design handbook, which I know you already know who are those people, right? They have produced, but it's like 110 pages, and every time that you go to a design board, you have to be reviewing, right? So small capability from a vendor, what are your capabilities? That's first, right? And then is what you prefer. And then we need to really match you prefer so that we don't have to be talking about. But if we go outside from that boundary, we need to go ahead and talk about one-to-one. Otherwise, when we do a full layout, full design, and then you say, that's not really our capability, we have to retouch one more time, and it's burning out, really. So the best way is also to know the DFM rules so that it's a win-win situation when we send something, That's all.
Okay, thank you so much. We'll do that.
Sorry
Thank
to
you.
interrupt. We already have that clearance document, Lucy. It was sent to Amit.
All right,
Maybe
I'll make sure
that's-
I approve that. Yeah, we
Yeah.
don't have to talk about that on a webinar though. Thanks though.
Okay, next question. For silkscreen, what is the smallest readable text size? That's a good question.
Really, it's just what resolution. I want to say it's 25 mils high and 4 mils wide. Is pretty much the standard. That's using the inkjet technology. And that's just typically limited to white. If we have to hand screen it, it's got to be bigger, and I don't know the restrictions right off the top of my head.
Okay. Any other questions? Anybody wants to unmute themselves and talk to us? If so, raise your hand.
Yeah, one thing is in silkscreen. In silkscreen, we're talking about the aspect ratio, line stripe versus height. That's also important because if you have too thick, the text is not readable. So IPC rules also too, they have some minimum also too, which is more than whatever you're expecting there. Sometimes they prefer an aspect ratio thing, but like whatever you're saying, 25/4 is around 6, the aspect ratio. So the thing is, as a producer of board, basically how really the tech need to be, the minimum. That's what I'm saying, the minimum. Because in crowded boards, it's very tough really to put all the silkscreen, right? So that's why we always look for the minimum, and we try to go with your suggestion because you have plenty of board going through. You know what basically your minimum, what's your maximum, for readability on text. That's all.
Okay, thank you. Well, it seems like we no longer have any questions.
I say one more here that we can answer real quick. Best materials for class 3. That's usually spelled out in the class 3 specs. It really has to do with how much temperature the board has to withstand. We see a lot of class 3 material, or a lot of class 3 jobs come through with polyamide material spec'd out on it. So it really has to do more with what the board has to withstand than.
Okay. Thank you. Thank you, Amit, for presenting. Thank you, Vandana, for the demos. Thank you, Steve, for answering the questions. And thank you to everybody who joined. Have a great day. Bye-bye, everyone.